only went to bed at 1 a.m. And I also got up at 7 a.m. Just not enough coffee today. Right, ideal gas law. Got that? Yep, ideal gas law. So, let's have a look now. It's a good bit to be doing. I don't know if we'll do it all now, but we'll see how much we can get done. Boyle's law. Maybe somebody's heard of Boyle's law. You know it? George, what do you think it is?
I just remember.
I'll go on, give it a go. What do you think Boyle's law is? I'll give you a clue. The word proportional is in it. Something is proportional to something. No, don't even want to try.
Too many golden hearts.
Okay, fine. So, Boyle's law says that for an ideal gas, P is proportional to 1 over V, provided that everything else is constant. So, what Boyle basically said is, if you make the pressure bigger or smaller, you affect the volume in this particular way. So, if the pressure is twice as big, it's because the volume is half the size. So you can do it the opposite. You can say if you make the volume twice as big, then what happens to pressure? It'll be half as big. So that's what Boyle figured out, that the pressure and the volume has this what's called inverse relationship. You can write it as a formula using this symbol, proportional. P is proportional to 1 over V. So it means that the P is twice as big, then the V is half the size. Or the opposite, if the V is twice as big, then the P is half the size. Another way to write it is that P times V is a constant. Simply put, Boyle noticed that if the volume is halved, then the pressure is doubled, or vice versa. Okay, I think you need to write all of this, everything. Well, maybe not that much. You wrote down already, Andrew?
Yeah.
Oh, great. What's for lunch today? Off to the mosque?
Maybe to the pizza place.
Pizza place?
Yeah.
Pinheads?
Is
That's the pizza place at the corner?
Yeah.
Yeah. It's nice, I've been there a couple of times.
Yeah.
It's nice. Good pizza, good burgers. Huh?
Yeah, never knew it. Yeah,
Me either. I just know it as the pizza place.
The pizza place. Place you go for pizza. Yeah.
Even my whole family says it's a pizza place.
Yeah, everyone says pizza place.
So there can't be many pizza places nearby if that's the only one people go to. Oh, I saw yesterday on the news that McDonald's is now doing deliveries.
What?
Yeah. Yeah. I think the one in Rathmines, Dublin 6.
They didn't deliver?
Huh?
They didn't have delivery?
No, it started yesterday. Have you already had it in your home country? Yeah.
The most important
Delivery.
Yeah, 24 hours.
24-hour delivery. What?
Yeah.
They close only from 5 to 6.
Is that mosque time or something?
Just 5 a.m. to 6 a.m.
Oh. Why that? For some reason? Change staff maybe?
Yeah.
A little interesting fact. Boyle was Irish. Did you know this? And he's actually buried very near the school, if you can believe that. If you go out towards the traffic lights, where the pizza place is, and as you're walking to the traffic lights, turn left at the traffic lights, and if you walk down this road, there's a big church on your right. Do you know the one I'm talking about? Yeah. This is where he's buried. So you can actually go visit and see his grave if you like. I haven't actually taken students down there, but it's only 10 minutes away. So you heard of Boyle before, so this, you now know where he's buried. He's not far away. Okay. Are there other relationships between pressure, volume and temperature? There are. So it will not surprise you to know that temperature and pressure are related. What do you think the relationship is between temperature and pressure? How do you think changing one affects the other? Directly proportional, yeah. Because if something gets greater temperature, so that the pressure will be increased. So you know from day-to-day experience that if the temperature increases, then the pressure increases until kaboom, something explodes. So you actually have this particular graph here. I just actually, before I show you that, I'll just draw it here first. So I'll just put the temperature here in Celsius, and I'll put the pressure here, temperature in Celsius and pressure in pascals. Okay. Now there's an experiment you can do. So let's imagine you have some oxygen, and you put the oxygen at one particular temperature and you measure its pressure, and there it is there. And then you increase the temperature, and what happens to the pressure of the oxygen? It increases, and then you continue like this. So let's just imagine that's oxygen, okay? So you can draw a straight line here. Now let's say you have some other gas like nitrogen. So you put nitrogen at a particular temperature, and maybe its pressure is higher than oxygen's at that temperature. And then you increase the temperature, and what happens to the pressure? Increases as well. So you get this. And then you do it for some other gas as well. And for some other gas as well. What you notice about these graphs is if you were to draw if you took the data and made a line, but drew the line backwards, they'd all intersect at one point on the axis here. And you realize you can't actually be beyond this because the pressure would be negative. And you're not allowed to have negative pressure. So we'll have to delete this and delete this. Okay. So it's quite interesting that no matter what the gas, that there's only so far back you can push the temperature. This point is minus 273 Celsius. So this was actually done. Well, who do you think did this experiment? Not Boyle, although that would be nice, it wasn't Boyle. Who do you think did this experiment? I think if you look at this number, you might figure it out. No, the other guy, not Celsius, the other fella, Kelvin. Kelvin did this experiment. Kelvin might have been Irish as well, actually. I have to check that. He might have been Irish as well. Kelvin did this experiment, a long time ago, and using his data, he was able to figure out what the minimum possible temperature is, and you cannot be below this. It's quite an achievement. He figured out there's an actual limit to how cold something can be. It can't be any colder than this. So this is the limit. So Kelvin noticed this, and he called this point absolute zero, the coldest you can possibly be. So this is actually a very important graph. I think what I would like you to do is actually to make a copy of this graph. Quite an important graph.
There's no negative pressure.
There might be some weird quantum negative pressure, but really, no. Like the space is like sucking in on itself or something. Like there might be some weird thing like this, but not really for normal gases. Maybe in Star Labs or something, but You got my DC reference?
Yes.
Yes, okay, good. Does Marvel have a version of Star Labs?
for, I guess.
Oh yeah, yeah, no, that'd be true, yeah, yeah. Have you got this? Siva, do a quick Google of where Kelvin was born. I'm curious now. I think he's Irish. Have you got this? Yeah, continue. Oh, that's going to put a pizza plan problem in place.
But the reason he is not in the Sweden.
Belfast.
Not too bad.
Yeah.
Where?
Belfast.
Belfast, okay, Northern Ireland, great. Okay, so the definition of absolute zero, you've done this in chemistry, haven't you? No. Minus 273, hasn't come up yet in chemistry. Absolute zero is the lowest possible temperature any material can be at. Okay, so because of this, Kelvin figured out actually, because this is the smallest possible temperature, maybe it would make more sense to use a scale that starts at absolute zero. So we have this scale, it's called the Kelvin scale, and it's the same as the Celsius, but everything is increased by 273.15 units. So for example, minus 273 Celsius is 0 Kelvin. Minus 272 Celsius is 1 Kelvin. It's just the difference of 273. So in the Celsius scale, the coldest you can be is minus 273. In the Kelvin scale, the coldest you can be is 0. So they're nearly the same. They're just moved by 273 units. That's all there is. So if you want the temperature in Kelvin, it's just the temperature in Celsius plus 273.15. You haven't done this in chemistry yet? Alright, I thought you would have done it by now. Got it? Yep. By using Kelvin, the temperature is always positive. Kelvin's always a positive number. Now, here's the technical definition of Kelvin. The Kelvin is a scale of temperature with absolute zero as 0 Kelvin and the triple point of water as 273.16 Kelvin. So just to be clear, when you want to make your own temperature scale, you have to define 2 points on the scale. So for Kelvin, the 2 points are this. You begin at 0, that's absolute 0, that's 0 Kelvin, and then 273.16 Kelvin is the triple point of water. Now, you haven't heard what the triple point of water is yet. It's a very special state of water, which we'll have a look at in a minute maybe. But this is the formal definition of the Kelvin scale. Now, I really would like it to be as simple as this formula, but this is actually the definition for the exam, I'm afraid. So if you can write this down carefully. You got that definition? Yeah? Yeah? Okay, so just before we do that, I just want to say what the triple point of water is. So, you know that water can be a solid, a liquid, or a gas. Okay, so when is it a solid? When the temperature is less than or equal to 0 Celsius. But since we're using Kelvin, maybe we should use Kelvin. So it's a solid when the temperature is less than or equal to 273.15 Kelvin. When is it a liquid? When the temperature is between 273.15 Kelvin and 373.15 Kelvin. It's 100 Celsius. And when is it a gas? When the temperature is more than 373.15 Kelvin. Now, these numbers actually, you can change these. You know, if you change the pressure, like in this room right now, the pressure is not 1 atmosphere, it's a little bit less than 1 atmosphere. That actually affects the boiling point of water. The temperature when the water boils actually changes a little bit. So, if you try to make a cup of tea at the top of a mountain, the point at which the water becomes gas is changed. And you can actually do other things to change the boiling point. I think if you add a bit of salt into the water, you can affect the freezing point and the boiling point, okay? So, the triple point, no, it's not 2 P's in triple, is there? It's 1 P, what am I doing? If you get everything just right, if you have the right amount of pressure, if the water is not containing any salt, you know, if you have all the conditions right, the triple point is when the water is a solid, a liquid, and a gas at once. And this happens at 273.16 Kelvin. So if you get the temperature to be exactly 273.16 Kelvin, and if you get the right pressure, I'm not sure what it is, but if you get the right pressure and the right temperature, which is this, and no salt in the water, you can get the water to be a solid, a liquid, and a gas at the same time. And if you wonder what on earth that looks like, to be a solid, a liquid, and a gas at the same time, you should go to YouTube and type in triple point of water. I've seen some videos of people pouring this. It looks quite crazy because they pour it and it looks like a solid, but then it's also a gas and it's flowing like a liquid. It's quite interesting to see. So after this lesson, take out your phone and type in triple point of water. You can see somebody demonstrating what the water looks like. Okay. Now you don't need to know this for the exam. You just need to know this definition for the exam. But if you're wondering what the triple point of water is, it's a special point when it can be solid, liquid, and gas at the same time. Are you having a look for a video? Yeah, have a look. Type in triple point of water, and then once you look at a video, we'll finish there, okay? We'll continue next time. So just put in triple point of water. See if you can find a nice video.